So we stopped at two antenna arrays. Sorry, we stopped at antenna arrays where we understand what is antenna array. For example, we stopped at here. Interface control, relation pattern control, destructive interface, weak interface. This is the entire reason antenna arrays are powerful. With an array, you can control number of elements, spacing, relative current amplitudes, relative phases, and therefore control the radiation pattern. So, an important term array factor. When studying antenna arrays, you will encounter array factor. Don't be scared by the name. It basically tells us what radiation pattern is produced by the arrangement and excitation of multiple antennas. For an array, we often separate total radiation pattern equals to element pattern into array factor. So total radiation pattern is element pattern into array factor. What radiation pattern is produced by the arrangement and excitation of multiple antennas. So we put an arrangement of antennas, group of antennas. They are excited, multiple antennas excited. Then total radiation is element pattern means the order of the element pattern and the array factor. This is a very important antenna array relationship element pattern. What one antenna can be produced by itself. What one antenna would produce by itself array factor. What the arrangement, spacing, amplitude, and phases of multiple antennas produce. Element pattern. What is element pattern? What one antenna would produce by itself. So this is one antenna can produce by itself. This is what the arrangement or spacing or amplitude and phases of multiple antennas produce. Like this is array factor, arrangement or spacing, spacing and amplitude. Example, suppose we have two identical dipoles, dipole 1 and dipole 2. The distance between them, this is two array. The distance between them is d. Each dipole has its own radiation pattern, but when they operate together, their fields interface. Therefore, the final pattern can become one broad loop, or it can develop multiple loops depending on spacing and phase. This is why arrays are used when we want more directional radiation. Where this occurs in real life, antenna arrays are everywhere in communication systems. For example, cellular base stations, radar, satellite communications, 5G, massive MIMO, phased array radar. A base station can use many antenna elements and control their phases so that radiation is stronger in desired direction. That's essentially the practical power of antenna arrays. What we should study next for ourselves, we should study next element array, spacing, phase difference, concept to continue. So starting with two identical antennas, imagine two identical antennas separated by distance d. Both antennas are transmitting. Now imagine a receiver far away at the same angle. Antenna 1 and antenna 2 receiver is here. The wave from the two antennas travel toward the receiver. The first important thing is path difference. First important thing is path difference. The receiver is generally not the same distance from both antennas. Therefore, one wave travels a little farther than the other. The extra distance is called the path difference. For a simple two-element array, delta equals to d cos theta, depending on how theta is defined. It's important some textbooks define theta from the array axis, or others define it from broadsides, so don't memorize the cosine blindly. The geometry determines whether you get cos theta or sin theta. So, mm, two-element antenna array and here, the first element path difference. The receiver generally is not the same distance from both antennas. The receiver for an antenna 1 it is not same distance. From antenna 2 it is not the same distance. Therefore one wave travels a little further than the other. Therefore, like this is nearby, let's say this is nearby antenna 2. It travels very fast than this travels. Uh, then why is there angle from the extra distance is called path difference. So from antenna to antenna 1 has a distance. If you do antenna 1 distance to antenna 2 distance, you'll get a path difference, right? Or simple two element array delta equals to d cos theta. Then why he said d cos theta, depending on how theta is different. Why different theta? Why path difference? Let's say a complete path difference creates phase difference. He is talking about phase here. Use array factor. Why this? Let we set two antennas, path difference. Then simply we can put like antenna one, two receiver distance minus antenna two, two receiver distance equals to path difference. So my logic, your reasoning is correct. If you know the actual distances from each antenna to the receiver, then the path difference is simply delta equals to R1 minus R2. Or if you only care about the magnitude R1 minus R2, where R1 distance from antenna to receiver, R2 distance. So why did I wrote d cos theta? Because in antenna array problems, the receiver is usually assumed to be very far away from compared with the spacing d distance. Imagine antenna R2 are separated by distance separation. You could absolutely calculate R1 minus 2 if the actual R1 and R2 are given, but usually the problem doesn't give those two huge distances, instead it gives antenna spacing, observation angle, theta. Then, um, geometry let us approximately the difference, approximate the difference as delta e approximate equals d cos theta. For a particular definition of theta, why is the approximation possible? Because the receiver is far away, for example, d equals to 1 meter, but the receiver might be r equals to 1000 meter. The two paths might be, for example, d equals to 1 meter, r equals to, what is r here? The distance from separation d. Okay. But the receiver might be r equals to 1000 meters. The two paths might be r1 1000. You don't really care about the enormous common distance of 1000 meters. What matters for the interface is R1 equals to R1 minus R2 equals to 0.4 meters. The difference is written by the geometry of d theta. Okay. So this is R1 antenna distance from receiver. The if two antennas are connected, the diagram is slightly wrong. R1 is connected to receiver. R2 is connected to receiver. Then R1 distance antenna to receiver, antenna on to receiver is R1. So by doing R1 minus R2, we get 0.4 meters. But we can actually get this by using this formula d cos theta, where for example d equals to 1 meter. So here my doubt is what is d actually? If R1 is distance from antenna onto receiver, and R2 is distance from antenna to receiver. Then what is separation between? Is it okay? Which distance between the two antennas? Between two antennas, each other. Okay, that's the consider. Okay. D is the distance between the two antennas. We given in the problem also. D is the distance between two antennas. Okay, okay. Then how will we know cos theta? How will we see know cos theta? Is forms an angle with the is it the three antennas form an angle like uh, acute or something? How will angle can be known? As d is simply the distance between the two antennas. We have the part exactly right. The config is about where theta comes from. Let's build it from scratch. A1 is and A2 antenna 2 is separated. B is the distance between two antennas. It has nothing to do with the receiver. Now put the receiver somewhere. Then R1 is R2. Now we have 3 points. A1, A2, receiver. As from the form a triangle, the two sides of R1 to antenna D1. Then where does theta come from? This is where antenna diagrams can be confusing. We define an observation direction. Suppose the array is horizontal, array axis. Now imagine a line pointing from an array toward the receiver. But depending on the test case, maybe theta may be measured from the array axis or the perpendicular broad section. That's why you see d cos theta, d sin theta. They are described the same geometry. The easiest way to understand is forget the formula for a minute. What part of antenna separation d lies along the direction toward receiver. That projected distance creates the path difference. Imagine projecting d on the receiver direction. So we are projecting d on the receiver direction. So this is your d. This is the receiver side. So what we'll do, these two are antennas. Suppose these two are antennas and the distance. We'll make the distance fall on the this side here. Then the acute angle, the angle theta will form here. Receiver direction, the projection d cos theta. Special case receiver exactly broadside. Suppose the receiver directly perpendicular to the array. Both antennas are essentially the same distance from the receiver. R1, then delta 1 R1 minus R2 equals to 0, so there is no path difference ratio. That's a very useful result. Cos 90, right? Cos 90 is 0, so operations is 0. If you are moved toward the end of the array, now one antenna is closer than the other. R1 is not equal to get a phase difference rather than the important entry picture. The three antennas form some random triangle and have to find its angle. We fit this observation direction. Okay, so we simply know if we projected this here, It's forming 90 degrees. Here or here, it's forming 90 degrees. Mm, suppose we form it here. This is two distance antenna D. We form it at the receiver side here. Then R1 to this angle is it's really confusing. Okay, like you said, to put the angle arrow like you said, like take D as a page 40 page at receiver side. Now check the angle between uh, somewhat from R1 or R2. If you are asking exactly the which two lines define theta, if your angular diagrams are often cause confusion, let's do one of conversion and fix it. Take the angle from the array axis, okay, and in a two. Reveal the distance between two antennas. The horizontal line to the two antennas is the array axis. Um, so this is the horizontal line is the array axis. The slanted line toward the receiver represents the observation direction. So this is the observation direction. Theta is the angle between the array axis and the direction toward the receiver. So theta is the angle between D direction and the receiver direction. Theta is the angle between D to receiver direction. Okay. So like receiver to theta. Why not here? We put this side line, then it's a different angle. Uh, did the same angle? I don't think so. It, this is rock this side. Theta. Mm, but but we look at this. So the same theta angle will be different. Now theta will be different. We look at from other end of this, right? That's not it. As exactly found the important issue, the numerical value of theta depends on where you choose the direction reference direction. That means the picture. First, receive the theta. Here, theta is the angle between array axis and receiver direction. If we take left the direction, if we take left the direction, antenna 1 to antenna 2, that's 190. Um, Now, the angle measured from the same left the direction is not same ordinary acute angle. It is on the other side of the axis. Here, you have to specify what direction you are measuring theta from. But here in the key antenna convention, we don't randomly change the reference from one antenna to the other. Hmm, what the hell is it? Is it in the middle? No. But here the key antenna convention, we don't randomly change the reference from one antenna to the other. We normally define one fixed coordinate system, for example, even A2 plus x-axis, D then define theta, angle measured from axis. So for the first receiver, 0 is less than theta is less than 90. For the receiver directly along the plus x direction, theta is at 0 degrees. For the receiver directly perpendicular to the array, theta equals to 90 degrees. For the receiver toward the minus x direction, theta equals to 180 degrees. We don't change the reference that displacement. It is on the other side of the axis. Reverse confusing actually. What is this concept called antenna array? Antenna array, d cos theta, theta is path difference. Antenna d cos represents the exact distance path difference over travel from multiplying this path difference by propagation to a theta. I got it out. How theta is measured. The linear antenna array, theta, is measured related to the line of the array itself, not the perpendicular broad line. Here, exactly how to visualize antenna 1 and antenna 2. This is the array axis, y in connecting the elements. Theta angle of arrival of departure. This is the theta angle from where wave direction far field. Use the end fire theta. When you are not saying you're making a difference, my doubt is saying saying if we calculate from antenna 1, then theta value is change. We're also to explaining the same thing. We are asking if you draw lines from antenna 1 to antenna 2 all the way to the receiver, then those two lines have different angles. Yeah, you are 100% geometrically. The receiver is close, the angles are different. However, we use a little concept called far field approximation because the receiver is extremely far away. Compared to the tiny distance b, the two lines traveling to the receiver becomes perfectly parallel while the angles stay the same. Imagine looking at the real road. Up close they are parallel, but if you look from miles into the distance, they seem to meet at a single point. The receiver, if you reverse the view from the distant receiver looking back at the tiny antenna array, the line coming to the antenna one and antenna particle practically parallel because they are parallel. Theta one equals to theta two. Okay. So the path difference is zero. So it they are parallel, the angles are parallel. So no problem from where we calculate. The angle will be the same from which one because it is near field we are confused. But when we calculate from the far field, the two lines are practically parallel. So theta value change. Here in the diagram it is showing very near. So that's what we conclude in the topic. Topic. So it is for here from there to here. Yeah, here. The extra distance is far different. This is important. This is important. Some tasks will define data from array access, while others define it from both sides. So, uh, uh, here and don't glitch. Path difference creates space difference. So this is this is important. Some tasks will define data from the array access, while others define okay. Path difference creates phase difference. So path difference theta delta creates a phase difference. A complete wavelength corresponds to 360 2 pi radians. 2 pi means 360. Therefore, if the path difference is delta, the path difference is delta. Path difference due to distance equals to 2 pi by lambda delta. Substituting delta phi path equals to 2 pi d cos theta by lambda. Again, assuming our angle definition gives delta equals to d cos theta. So a complete wavelength corresponds to 360. 2 pi. The radio wave is 360 now. The complete like how that a radio wave is calculated as wavelength of a circle. The circumference of such circle is 360. So 2 pi radians is 360. What is the wave? What are wave diagrams? Wave diagrams are nothing but waveform diagrams of a signal from its properties like current or voltage. So the entire waveform is length is mm, phases or total phases will be 360 from one cycle. 2 pi radians. Therefore, if the path is difference is delta, phase difference due to distance is 2 pi by lambda delta. Substituting delta phi path equals to 2 pi d cos theta by lambda. Delta value we got 2 cos theta in the here. So we substituted path difference due to distance. Again, assuming our angle definition gives delta equals to d cos theta, but there is another source of phase difference. That is, this is very important. The two antennas don't necessarily have to be fed with exactly the same phase. For example, antenna 1 equals to I1 cos equals to I0 cos omega t. Antenna 2 I2 equals to I0 cos omega t plus beta. The second antenna has initial phase difference beta. The total phase difference at the receiver is beta plus 2 pi d cos theta by lambda. This symbol is I don't know what it is. Progressive phase difference for this simple array geometry. What is beta? The second antenna has an initial phase difference beta. Mm, These are current equations. Like why you know there is a difference between two like phase difference. In AC current signals, we talk about lagging lead phase lag phase. This is lead phase current. and this will test mm, from antenna. It has some phase. This has some phase. Comparing both, this is leading I naught cos omega t plus beta. So beta is the initial phase difference. So the total difference phase difference at the receiver is progressive phase difference beta plus 2 pi d by lambda cos theta. Now you can determine whether radiation is strong or weak. If zero, then the waves are in phase, therefore constructed interference. More generally, 2 and 5 for maximum radiation. If this value is come, then the wave arrives opposite in phase, destructive interference. So more generally, 2n plus 1 by 2n plus 1 into 5 is the result. Where n is the oxygen, what is n. So by calculating this, we will get this value. This is constructive interference where n is what we do themselves. Where n is just an integer that defines which destructive interference conditions we are talking about. Total difference between waves from the two antennas, what values can take 0 plus 1 minus. Let's substitute n equals 0, uh, then phi equals to 180. The two waves are exact opposite destructive interference. Now n equals to 1, 2 1 plus 1 into 5 to 3 5 5 5 t. Again, the waves are effectively 180 apart because hypotenuse waves 180 destructive and effective. After the main compute 360 degree cycle, we over left is 180, so n equals 0 into 2, simply use the proportional and theoretical. Because 3 on 3, 5 are numbers, therefore, one is the maximum radiation. 3 and 5, which gives even multiples of 5, waves parallel the phase. Okay, now, mm, what's next? Why I use understand 2 pi by lambda because wavelength because total length of wave is equals or phase equals 180 degrees, so 360 degrees because the wave diagram on measure is circumference of circle. and vector. Yes, we're introducing, but this is very useful connection. The reason we use superlines for complete balances ultimately connect to the circle for the representation of sinusoidal. One complete cycle equals to 2 pi radians. So one complete cycle means like, this is one complete cycle like I am showing. This is one complete cycle. Two waves is a complete cycle. After one complete revolution, 360 degrees superlinear, the projection and the magnetic effect of sinusoid both 360 to parallel. Now connect to these two length lambda is physical distance over which the wave completes one full cycle. So the wave travels a distance lambda, its phase change 2 pi. If it travels only a half wavelength, lambda by 2, then it has a completed half wavelength, pi equals to 180. The quarter wavelength is 90. That's why we get this formula. Uh, what is a cycle? A cycle, imagine if you want to, this is one cycle, okay? This is one cycle. So starting at one point, following the waveform until it comes back to the same state and starts repeating again. This is one cycle. With one cycle, uh, for example, on complete cycle, after this, observe the same pattern starts again. If the voltage goes Vmax, 0 plus Vmax maximum voltage and comes to 0 and negative Vmax. And that one is completed cycle, one cycle. That's one cycle is a 2 pi. Uh, length of that cycle is one cycle is 350. 50 cycles per second means 50 edges. One third, if it completes 1030 means 1 megahertz. If RS is that's what is called frequency number of cycles per second. Mm. One cycle means one wavelength lambda. One cycle means one cycle equals to 360 2 pi radian. Lambda equals 360 lambda 2 lambda 5. Okay, now off next and off syllabus. I think which people something. Mm. Until the what happened start from that 2 5 3 5 even odd 5 which you are explaining and continue from there some more people. So on islands on complete cycle, this is including path difference. This is path difference. Mm. By lambda lambda, just simply act what's the action available and the extra distance delta with the path difference. Um, Therefore, delta phi equals to the lambda delta r and complete event corresponds to lambda people plot difference. Example plot difference lambda delta 350 delta reflection lambda major purple lambda by 2 with a cancel as 1 plus 1 rating minimum. This is even the pirate expression came from this symbol. Yeah. Talk about phase difference. We write the complexly as just symbol what is it? Which okay, forget. Waves are opposite in phase line 5 3 5 5 5 long. Mm. We connect this back to our antenna. Phase difference internal point of data. Phase difference caused by the day difference travel distance caused by the down. Then therefore this is data plus theta. Plane radiation, null radiation. There is broadside array and array. What is the symbol? What is this symbol? And we put something capital E some equals to capital E something like this. Go to this is literally an important step. Right before jumping to this 3 and 5. What is pi? This is Greek term C psi. In our antenna discussion, we represent the total field difference between the waves reaching the receiver from the two antennas. So it is a total phase difference. This is phase difference. That is path difference. We skipped this equation. Suppose identical antennas could be phase one equals to zero. Then the field from antenna 2 have a phase difference which equals to J phi. The total resultant field is equals to E1 plus E2. Therefore, E equals to E0 plus E0 equals J phi. Factor out E0 equals to E equals to E0 into 1 plus E equals J phi. This equation is called, this is the equation we remember. Why are we adding E1 and E2? Because it is Fourier superposition. Two electromagnetic waves arrive at the same receiver location. Their fields combine. E total equals to E1 plus E2. They don't remain separate, and because electromagnetic fields are magnitude and phase, we have to add them as phasors and not simply ordinary numbers. Now look at the special case, E0 plus E0 to E0. Therefore, phase difference is 0. The phase difference is 5. Remember, 5 plus 180. E0 for J5 is minus 1. If J means minus 1, because J5 means minus 1 is equal to minus 0. Again, it is here it is 2 here minus 2, so it is 0, complete cancellation. If 2 and 5, it becomes 2, 5, 4, 5, we complete 5 equals to enter and equals 0 into 3 by because these are all phase equivalent to 0 modular complete cycle for example. We have to remember this, we can just remember this, we can't remember this right, so we can just remember this. In place of 0, we have 0, 5. If you get 1, you get 2, 5. If you 2, you get 4, 5. So to remember that, this is the formula. So this is for odd numbers, 2n plus 1, if you remember this. And we do size itself function, 3 to phase difference, path point difference, size. It depends on the size. Continue next. Continue next, broadside answer. Okay, and fail. And fail. Okay, so what is now that we have the missing foundation broadside and infrared will be much easier. We have two antennas separated by distance d, and the total phase difference at the receiver is this psi equals to beta plus 2 by d by lambda cos theta. For our convention, where theta is measured from the array axis. Broadside array. First, understand the word broadside. Broadside means sideways to the array. Imagine the array is horizontal. The array is horizontal. The broadside direction is perpendicular to it. The broadside means perpendicular to the horizontal direction. Um, so we want maximum radiation at 90, theta equals to 90. What happens to the path difference here? Our path difference expression is delta r d cos theta. Theta equals to 90 means our delta r equals 0. This makes physical sense. Both antennas are essentially the same distance from a far away broadside receiver, R1 equivalent to R2. Therefore, there is no path induced phase difference. How do we make the wave set? We want maximum radiation. Maximum occurs when psi equals to n pi. At broadside, psi equals to beta plus 2 pi d equal to 0. Means psi is to beta. Therefore, for maximum at broadside, beta equals to 2 n pi. The simplest choice is beta equals 0. That means the two antennas are fed in phase, so broadside array elements excited in phase for the basic two element phase. So here it all depends on beta. Uh, for maximum and broadside, beta will be 2 and 5. The simplest choice is beta equals 0. This means two antennas are fed in phase. So broadside array, visualize it, maximum radiation. Both antennas will be waves that reach the broadside direction in the phase. Therefore, equal to 1 plus 2, then 2 E naught, and for array. So, and for means radiation is strongest along the axis of the array, our array. The end for directions are along the axis. This is perpendicular to the axis. This is along the axis. That's why it's called end fire array. That's broadside array. This end fire array, we want maximum radiation along the array axis with our convention theta equals to 0. Angle is 0, right? For the x-axis, now path difference theta equals 0, cos 0 means 1, delta equals to d. So one wave travels one extra distance approximately equal to d. That would this is a phase difference. Delta of path equals 2 pi d by lambda. Now we have here's the clever part. We can deliberately feed the antennas with a phase difference beta so that it compensates with at this path difference. Condition for end fire array psi equal to 0. Our equation is the cos theta equal to g 2 pi d by lambda. So beta equal to minus 2 pi d by lambda. This means we intentionally use the antenna's current phase difference that cancels the phase difference caused by the different path lengths. This is the beautiful idea behind an answer array. A1, A2 and receiver. A2 is closer to receiver, so A1 will have further to further to travel, that creates a phase one disadvantage. We compensate by giving A1, A2 an appropriate feed phase difference. Therefore, when they finally reach the receiver, their fields are in phase and we get maximum radiation in the direction, broadside versus underside. Basic theta equals 90, theta equals 0, path difference with 9 direction, 0. Uh, Here along the axis equals to d, here path difference comes 0. Basic feed, basic feed phase, where beta equals 0, here beta equals minus 2 is the feeding phase, use feed phase to compensate. Here we get, we did, we made the psi equals to 0, so beta equals to 2, beta equals minus 2 feed. Here then we should also do here psi equals to 0. Here, we get psi equals to beta. Here we did maximum occurs in 2 and 5. Here we get maximum occurs in 2 and 5. Here we did maximum occurs at 0. That's why we did 0, 0 minus 2. So that's my doubt here. We'll look into this later. Let's break a break. Next video we'll continue next video. We should do array factor maximum minimum. Is it in the syllabus? Was very wrong. The computation. I understood it was going away. My service with this why it is going into that container performance package. But I think we are going out of the the right to challenge me. We should not challenge maintain and arrays in their full and purpose. So it does not appreciate release terror after derivation to another derivation out of perfection side level analysis dynamic. Those service introduce some of this background to make the concept understand better analysis arithmetically. So completed next. The oral syllabus is completed, maintain arrays finished now. So let's finish maintain arrays at the conceptual level and move to the final. We finished maintain arrays right. Auto maintain array for multiple antenna sets facing the top difference. Basic rule of relative phase sensitivity. We do not need to continue into deeper array magnetic unless an actual exam problem is the phase space signal. It was making me annoyed. It's making me annoyed. It's making me annoyed. Making me very annoyed. Like, should I study this? Basic of real relative phase. Um, no, I will go for communication maintenance performance quality. Stop here, continue the next video.